In this video, we'll be covering section 6.3, volume by slicing. We have 4 objectives. We're going to start off by finding volumes of solids using what's called a general slicing technique. Then we will find volumes of solids of revolution using what's known as the disk method. And then we will generalize that into what's called the washer method. This will allow us to find the volumes of solids of revolutions that have holes in them. And then we will apply those methods to solids of revolution that are rotated about either the y-axis or maybe a different line. Okay, so let's start by talking about the general slicing technique. Back when we found the area of functions under the curve of a function, the way we did that is we would approximate the area by using a rectangle. We would slice up this interval into a bunch of rectangles and then use the area of these individual rectangles to approximate the area under a curve. So the rectangle was the object we used to approximate. For volume, the object we're going to use to approximate is a right cylinder. Now, when you think of a right cylinder, you probably think of this picture right here. This is actually just one type of right cylinder. This is a right circular cylinder. But the actual definition of a cylinder is much more general than this, and that's what is included here. So the basic idea for a cylinder is this. Imagine you have some region, we're going to call that region B1, and you make a copy of that, a congruent region to that. This is B2. And then you arrange them so that they are parallel to each other and they're oriented in the same direction. So essentially you just copy this and stretch it up. The cylinder just consists of all the points that lie on perpendicular lines between them, just making that into a solid. So this is actually a right cylinder. The reason we call it a right cylinder is because we're joining them with perpendicular segments. You could have an oblique cylinder where you have 2 congruent regions, but they're joined by not perpendicular segments, they would be joined by slanted segments. So this would be an oblique cylinder. We're not interested in this type of cylinder here. We want only right cylinders. So that means a box, a rectangular prism, is actually a cylinder because this base here is congruent to the one at the top. They're parallel to each other, they're oriented in the same direction, and all of the points in between can be connected with perpendicular segments. So this technically is a cylinder, just like this is, which kind of defies what we were taught back in elementary school. So these are going to be the ideal object to approximate the volume of an irregular shape. Now, the first thing we need to do is define what is the volume of a shape like this, and they all have the exact same volume formula. You wouldn't think they do, but every single one of them has the same one, and it is this. The volume of a cylinder is simply the area of one of the bases multiplied by the height. And that's true for all of these. So if we look at the box first, I guess, we know that the volume of a box is length times width times height. But that actually matches the formula you see here. Length times width is A, gives you the area of this base, and then we multiply it by the height. A cylinder, we should already know the formula for a right circular cylinder. We know that the area of the base is the area of a circle, which is pi r squared, which you see right here, and then multiply it by the height, and that fits this volume formula as well. So any cylinder, anything that fits the definition given above, its volume is the area of one of its congruent faces multiplied by the height, which is the perpendicular segment joining the 2 bases together. So how can we use this? Well, imagine that we have some irregular shaped region like this, and we're going to align it along the x-axis here. And then the idea is we're going to look at cross sections of this. So a cross section, just imagine a plane slicing down through this. You can think of it like the blade of a knife cutting down through it. And that cross section would create a region, a 2-dimensional region in here. And that 2-dimensional region could change depending on where we slice it, meaning wherever this x is. So in order to get this to work, we have to create a function. This new function is going to be a cross-section area function, meaning that you plug in an x, and it spits out the area of the given cross-section. And it needs to be able to do that anywhere along this segment AB. So I should be able to come down here, plug in a different x value and slice through here and get whatever cross-section you would get here, and you would get, if you plug that x into whatever this cross-sectional area function is, you should get the area of that piece there. So generating the a of x, that is really going to be the tricky part of this whole process. That's really the thing that requires the most work, is finding a function that will give you the cross-section at any particular point. So for now, just imagine that we have this function, that somehow it exists. So what we'll do then is we will partition the interval AB, just like we did back when we did the area under curves. And within each partition, we will define a width. We're going to use an equal width here. So delta x, same as it was before, just the width of each subinterval. And then what we're going to do is create a cylinder in that region to approximate the volume of that slice, that individual slice. Now, we already know the cross-sectional area at that point, so we'll take our test point, x bar k. We're using x bar here instead of x star just because the images that I had, the stock images, didn't have the stars on them, but those are the exact same thing as what we had before. It's just a test point, just different notation for the test point. So we plug that test point into our cross-sectional area, which gives us the area of one of the faces of this cylinder, and then we multiply it by the height of the cylinder, which is delta x. So this individual slice, its area would be the a function evaluated at the sample point multiplied by delta x. And so then we just do that for each individual slice. You can kind of think of this like a weird loaf of bread that we're going to slice it up, and we're going to find the volume of each individual slice of bread. So that would look something like this. Right, just a bunch of slices. Each of these are cylinders, not what we would have normally thought of as a cylinder, but it fits the definition that we gave at the beginning. And the area of each individual one is given by that expression there. So if I want to get an approximation for the volume of the region that we're looking at down here, we just add these up. So we add up all of the individual slices, the volumes of each of the individual slices. And just as before, if we want to improve the approximation, we increase the number of slices. In other words, we're going to take n, and we want to push it to infinity. We want infinitely many slices to get the exact volume. So we simply take the limit of this sum. And notice that sum is a Riemann sum. So when you take this type of a limit of a Riemann sum, it turns into a definite integral. So this integral will give us the volume of this shape. So this is what we call the general slicing technique. We slice it perpendicular to some axis, either the x-axis or the y-axis, and then we have some cross-sectional area formula. We integrate over that interval, whatever interval we define, a to b, and that gives us the volume of that object. Again, the a of x is still the tricky part. How do we get that? Okay, so this is just stating that again. The general slicing method says you've got to get this cross-sectional area function, and then you simply integrate it over the interval a to b. It is also critical to note here that the cross-sections have to be perpendicular to the axis that you're integrating along. And you'll see that when we start to get to the pictures. All right, let's take a look at the quick check that we have here. So this says, show that the formula given above for the general slicing method is equal to the average value of the cross-sectional area multiplied by b minus a. Okay, so what are they talking about here? Well, if you recall, average value of any function, in this case the a function, is equal to 1 over b minus a times the integral from a to b of the function, which in this case is a of x, integrated with respect to x there. This is the average value. Now, if we solve for this, meaning if I just get rid of this, move it to the other side, this shows us that the integral from a to b of a of x dx is equal to b minus a multiplied by the average value. This actually makes a lot of sense if you think about it. What this is saying is the volume of the shape should be equal to the average cross-sectional area times the width of the interval. So the idea is if I come back to the picture of this shape, there would be some average cross-sectional area. So maybe it's, I don't know, maybe it's this one here. And imagine that we just turn that into a cylinder, meaning I keep that cross-sectional area the same all the way so that the whole shape is actually a cylinder. Now, it doesn't look very good, but imagine that just being the same height all the way across. Each cross-section is the exact same, and each individual cross-section, its area would be a bar. Well, the volume of this blue cylinder that I've poorly drawn here, the volume would have to be the cross-sectional area multiplied by the height of the object. Well, the height of the object, since we were integrating from A to B, would just be the difference, B minus A. So that is the volume of this blue cylinder, and that is going to end up being equal to the volume of the overall shape, because this is the average of all the cross sections that you see here. So it is definitely a reasonable thing that this should be true. Okay, so let's try an example. It says, let R be the region in the first quadrant bounded by the coordinate axes and the curve y equals 1 minus x squared. So that's graphed up here at the top. Graphed 1 minus x squared here. It's a parabola, shifted up 1 unit, frowning. And then we're also bounding by the y-axis and the x-axis. So that encloses the green region that you see here. It says a solid has a base formed by R. Our solid has this as the base. And cross-sections through the solid, perpendicular to the base, are parallel to the y-axis and are squares. So what that means is we're going to be slicing this thing up so that our slices are parallel to the y-axis, which means they're going to be perpendicular to the x-axis, and the cross-sections are squares. So you can't really see that. The squares would be coming out of the screen like that. So to visualize that a little bit better, I've made it into a three-dimensional picture. The green region here at the bottom is the region that you see up here. And this purple line, that vertical line here, corresponds to the line you see over here. So we've kind of just rotated this around here. And so this is the base of our square, which means it's shooting out of the page the same distance. So this is it coming out into that third dimension. And so we're going to have those cross sections all the way across. So no matter where I slice, as long as I slice it parallel to the y or perpendicular to the x, and then draw this up, it is going to create a square cross section. So that's the setup. We're supposed to find the volume of the solid created there. So before we do that, let me show you a three-dimensional image where we can actually move this. Okay, so here we have both of the regions. This is our base region, and then this is the graph in 3 dimensions. So if I take this and I were to rotate it like that, now we're looking at the same picture. This region is the region that you see here. And this vertical line is the same vertical line you see here. But you can't see the 3 dimensions then. So that's why we rotate it down like this. And over here you can see if I move this, I believe I can move this. Maybe I move it here. That's the top point. Okay, so as I move that point, it moves my cross section on the other shape there. And you can see no matter where I slice, all of these slices are generating a square over there. And that's what gives us our three-dimensional solid. And this is also what makes it so easy to calculate, is that every single cross section is the exact same shape, which makes finding the A of x much, much easier. Okay, so let's go back. Okay, so to get our typical cross section, which is what's generated here, this is the one side of the square. So all we need to do is figure out how long this is and square that. Well, the length of this segment here is simply the function height. It's f of x. Right? The length of that perpendicular or purple segment there is this thing. So a of x is going to be f of x all squared. Because f of x represents the side length, so we simply just square that. So that means it is 1 minus x squared all squared. Now we can do the volume. So volume is the integral from a to b. Well, in this case, this is where the cross-section is really important here. We're slicing up in this direction. So that is what we're integrating. We're integrating from this point to this point. So it will be from 0 to 1 of a of x, which in this problem, there's our a of x. Oops. All right, so then we integrate this. In order to integrate this one, we would need to FOIL what's in the parentheses there. So we're not going to do it fully, but you can't do a substitution on this one because the derivative of this is not outside of the integral. So we would do integral from 0 to 1 of 1 minus 2x squared plus x to the 4th dx. And then do antiderivatives, which would give you x minus 2/3 x cubed plus 1/5 x to the 5th, evaluated at 1 and 0, and then the difference between them. So we're going to skip most of the math on this. I'm even going to stop integrating. The main thing that we're focused on right now is getting them set up, and then obviously getting to the right answer. So this one comes out to 8/15. So that is the volume of this region that you see here. Okay, let's try another one of these examples. So in this one it says, a solid has a base that is bounded by the curves x squared and y equals 2 minus x squared. So I've graphed those over here. X squared is the basic parabola here, and then 2 minus x squared is a parabola shifted up 2 units but frowning. To find the points where they intersect, you would just set them equal, set each of these equal to each other, and you solve, and you get 1 and -1 for those. All right, so then it says cross-sections through the solid perpendicular to the base and parallel to the y-axis are semicircular discs. So again, down here we've got our cross-sections coming out of this would be semicircles. Perpendicular to the region that you see here would come out as semicircles. And you see that down here. So we're supposed to find the volume of that solid that's created. Again, let's see this in motion before we actually do that. Okay, so here we have the region. Here we have our cross-section generating a semicircle over here. So let's move this across. So on this one I have it tracing out each of those semicircles, which will give us a better view of this region that's being generated here. And so you can see, reminds me of Velveeta shells. So each of those individual cross sections is just a semicircle. Okay, so let's find the volume. So before we find the volume, I guess we need the area function. So area, well, we know that area is going to be 1/2 pi times the radius squared. It's semicircle, so it'd be half of a circle. So we just need to figure out, well, what's the radius of an individual cross section for this? So if we come back over here, here's my typical x, just a random x on my interval that I'm integrating across, and the radius would be this segment here, or it would be this segment here, either one of those two. Well, let's start with the top one. To find the length of this, what we would need to do is to take the y value here, which would be this, and subtract it by the y value here, the difference in the two y values. So that would look like 1/2 pi times the outer distance would be 2 minus x squared minus the inner. You can think of this like we did before. When we were doing area, it was upper curve minus lower curve. Well, this is upper and this is lower. So upper minus lower. That whole thing there is the radius. And then we have to square that. Just upper curve minus lower curve. If we simplify that, that's 1/2 pi times 1 minus x squared squared. Now, we could have also found the length of this piece, and you see you get the exact same thing. I said the length of that segment has to be upper minus lower, and that is exactly 1 minus x squared. So either one of those, whether you did the top radius or the bottom one, gives you the exact same expression. Okay, so volume is going to be the integral from, in this case, we're slicing, again, perpendicular to the x-axis, so from here all the way over to here. So -1 up to 1 of that expression. 1/2, let's just put it as pi over 2, times 1 minus x squared dx. Now a couple things we could do to make it a little easier. We can pull the pi over 2 out, and this is an even expression, right? It's symmetric on both sides, so we could double this integral and just integrate from 0 to 1. So pull the pi over 2 out, put a 2 in front of it, integrate from 0 to 1 of 1 minus x squared dx. This doesn't have to be done. You could just integrate this, but this would make the computation a little bit cleaner. So obviously these cancel here, and you just get pi multiplied by the integral from 0 to 1 of 1 minus x squared dx. Well, if you're paying close attention, this should look familiar. We just did the exact same integral a second ago. So this would be pi multiplied by the previous answer, which was 8 over 15. So this is 8 pi over 15. Totally different region, totally different geometry to it, and yet had the, it's just a multiple of the previous one, just pi multiplied by the previous answer, which is kind of crazy that that happens. All right, let's try one more of these. So this one was a quick check. So we're using the same exact region, but now instead of doing cross-sections that are semicircles, we're going to do cross-sections that are squares. So kind of a combination of previous problem and the first problem. So let's generate the area, cross-sectional area. So we know it's just side length squared. The side length would be the length of that purple segment. This is your typical x value. However long this is would be the side of the square. We just need to find that length and square it. So the length of this segment, just like the previous one, should be upper minus lower. So it's going to be 2 minus x squared minus x squared. Upper minus lower. So this is just the length of the purple side. To find the area of the square, we have to square that whole thing. So if we simplify this, this is really 2 minus 2x squared squared. Now I could factor a 2 out of this, but to pull it all the way out, I also have to square it. So that would come out as 4 times 1 minus x squared squared. All right, so now we are ready to do the integral to find the volume. So volume is equal to the integral from, again, we're slicing from -1 to +1, of a of x, which in this case is just this. So 4 times 1 minus x squared dx. And we could go ahead and just integrate, but as with the previous problem, we can simplify this a bit. So I can pull the 4 out, but I could also, since it's even again, I could change this from 0 to 1, but then I have to double that. So again, all these steps are optional here. So that just gives me 8 times the integral from 0 to 1, 1 minus x squared dx. And once again, same integral we have here. So this is 8 times the volume of the first one. So 8 times 8 over 15, which is 64 over 15. So again, totally different region. Yes, it does have the same base, but you can see changing the shape, the cross-section, whatever individual cross-section you're getting, just seems to give it a scalar multiple of the original one that we found. Okay, so this is the basic idea behind the general slicing technique. You will see examples where the cross-sections might be triangles. They could be, just an isosceles right triangle instead of a square. Or it could be equilateral triangle, something like that. So you'll see a lot of variation, and you'll have to remember some of your geometry in order to come up with these A of x formulas. This is usually where the trouble is just getting the formula for that cross-sectional area. So let's move on to a different way of calculating the volume. So we want to look at solids of revolution. So to generate a solid of revolution, imagine that you have a function. So here I have f of x, and I'm interested in the interval AB for that function. So that determines a region, an area like we would have had before. So imagine taking that area and rotating it about the x-axis. And imagine that as you rotate it, it sweeps out a solid. So that would look something like what you see here. Take that region R, start rotating it around the x-axis, and it generates what we call a solid of revolution. So we want to find the volume of something like this. Well, technically, we're going to use the exact same strategy that we had before. We're going to form a cross-section, and the special thing here is that each of these cross-sections, horribly drawn here, would be circles. So whenever you're generating a solid of revolution, the cross-sections always have the exact same area formula. They're always just pi r squared. So that's what this is actually explaining here. Cross-section is always a circular disk, so the cross-sectional area is always pi times the radius squared, and when it's arranged like this, the radius is just the function value itself, right? F of x determines that point, right? That distance right there is the value of f of x. So in this picture, radius is f of x. So pi times f of x squared would give you the cross-sectional area for a region rotated about the x-axis. So if we have a of x, we can write down the formula for the volume of that solid, which would just be the integral of the a of x formula, which would look like this. And for me, I will typically go ahead and just pull the pi out as well. It doesn't have to be pulled out, but that would be the same thing as well. So that is what we oftentimes call the disk method, just because the cross-section looks like a circular disk. Alright, so this is stating the same thing. So let's try just generating some solids of revolution. Hopefully my drawing skills don't make this horrible, but it says that on this first one we want to try to identify what solid is being created by this. So let's plot these vertices. We've got 0, 0, we've got 0, 2, 2, 0, and 2, 2. So that obviously gives us this square. So then imagine if we take that square and we rotate it about the x-axis. Well, if we do a half a turn, that square is going to come down here and create a copy of itself. But as it rotates, it should be creating, oh, that's bad, creating a cylinder here. So just a normal right circular cylinder. So that's what's created on this one, a right circular cylinder. All right, let's try the next one. We'd have 0, 0, 0, 2, and 2, 0. So this is a right triangle. If we rotate this one about the x-axis, then a 180-degree turn gives us a copy of itself. And you can see that this one is going to generate a cone. So we had a right circular cylinder on this one and a cone on that one. Okay, so let's actually do one where we actually find the volume. So this one says, let R be the region bounded by the curve x plus 1 all squared, the x-axis, and the lines x equals 0 and x equal 2. So we've plotted all that here. We got the function. It's a parabola that's been shifted to the left 1 unit. And we also have vertical lines, x equals 0, and the vertical line, x equal 2. So this is our region. We rotate it about the x-axis, and it's going to create this kind of horn-like region. And obviously, the cross-section, typical cross-section, is just a disk. So we know that the volume is going to be the integral from a to b of pi times the function squared dx. So first, identify the limits of integration. We're slicing it up like this. Each cross-section is perpendicular to the x-axis, so we're integrating from 0 to 2. And then I'm going to go ahead and put the pi out in front. And then inside we just need to put the function, but we have to square the function. So it's going to be x plus 1 to the fourth. All right, we square this function. That's going to be to the fourth. Okay, to integrate that one, substitution method would work nicely, but we're skipping the computations here, just going right to the answer. This should come out to 242 pi over 5. Now, as you know, ideally, I do want you trying to do these by hand, but if you need to check something in your calculator, the trick is leave the pi out of the computation. Enter just this part into the calculator, convert it to a fraction, and then multiply that answer by pi. Your calculator should be able to handle that. Okay, so let's generalize this. So the next thing we want to look at is called the washer method. So in this type of problem, what we're looking at is the region that we want to rotate, maybe it doesn't go all the way to the x-axis. Maybe it's bounded between two curves. If we were to rotate a region like this around the x-axis, we would end up with a hole, a hollow portion in the center. So the cross-section that you would get would look like a washer instead of a disc because it has a missing hole in the center. Now, the basic process is really the same thing as before. We just need to find the general cross-sectional area. We need the area of this washer. Well, any washer type region, you can find the area by finding the area of the big circle, which in this case would be pi times the outer radius, or the big radius, which I'm calling capital R, squared. And then you find the area of the inside circle, which would be pi times the inner radius. This would be the inner radius. I'm calling that little r squared. If you take the difference of those two circles, the big circle and the small circle, that is going to give you the area of that washer, our cross-sectional area. If we take that back over to this figure, well, the outer radius is the length of that segment, which would just be f of x, right? That line, that length of that line is f of x. The inner radius would just be this distance, which would be g of x. So outer radius is f of x, inner radius is g of x. So if we plug that into this expression, pi times outer radius squared would be pi times f of x squared, minus pi times the inner radius squared would be pi times g of x squared. I've gone ahead and just factored the pi out, so we don't need it technically on both of them. That gives us our a of x formula. So to get the volume, obviously we're just going to do pi times the integral from a to b of this. Outer radius squared minus inner radius squared. So this is what we call the washer method. Now, the washer method really is the exact same thing as the disk method. It's just that in the disk method, g of x is 0. If I replace g of x by 0, then that whole thing would just give us the formula that we had before. Integral from a to b, pi times f of x squared dx, because we'd be subtracting 0. So this is what I mean by saying that washer method is really just a generalization of the disk method. So let's try that with this example here. So it says the region R is bounded by the graphs of f of x equals the square root of x and g of x equals x squared between 0 and 1. We want to find the volume when it's revolved about the x-axis. So we've got those graphs plotted here. We've got the square root of x, we've got x squared. You would need to find where they intersect. You could find that by setting them equal to each other and solving, but in this case it should be obvious they're equal when x is 1. We're taking this region, we're rotating it about the x-axis. So when you do that, it would generate a region that looks like kind of like a bowl, but the inside of the bowl would be strangely shaped there. So that's the volume we're trying to find. Okay, so in order to do that, let's identify what the outer radius is. I think it's always helpful to write these down first. Outer radius would be the function, the higher function, the function that's on top, which would in this case would be square root of x. So that means inner radius is x squared. So volume, actually let's switch back to blue. All right, volume would be the integral from, look at how we're slicing it. A typical cross section is right here, perpendicular to the x-axis, and we're starting our slices here and we're ending them here. So they're from 0 to 1. We know we have a pi, so I'm going to go ahead and put that on the outside. It is outer radius squared minus inner radius squared. So square root of x squared minus x squared squared. All right, we're not going to fully do it, but let's at least simplify it a little bit here. This is pi times the integral from 0 to 1 of x minus x to the 4th dx. And I trust you can evaluate that one. That should come out to 3 pi over 10, I believe, which is the volume of the bowl type region that you see there. Okay, let's try a modification of this region. So this quick check, we're using the exact same functions that we had before, the x squared and the square root of x, but we're not going to rotate it about the x-axis now. What we're going to do instead is we're going to rotate it about x equal -1. So imagine we extend this down. Let's say this is -1 here. And we want to rotate around this. So the problem actually is not asking us to find the volume, it's asking us to write down what is the inner radius and the outer radius. Okay, so the inner radius would be the shorter radii, so that would be this distance here. I'm just picking a random x value, but this blue segment would be, the length of that segment would be the radius. There's a couple ways you can actually think about how to find the length of it. One is to always just do upper minus lower. So in this case, upper would be the function value g of x, minus the lower would be -1, the line itself. You can think of this line as, think of it as being a function. This is y equals -1. So upper minus lower should give you the length of that. So g of x in this case is x squared. So x squared plus 1 is the length of that blue segment. The other way you could think about it is you could think of it as two separate segments combined. So it's this green segment, which is g of x, plus the length of, let's do purple here, plus the length of this. And how long is that? Well, we know this is 1 unit long here, so it's g of x plus 1. That's another way to think about it. I do think the safest thing to always do is just upper minus lower, but either way works. Okay, so that's the inner radius. Let's do the outer radius. Okay, so let's actually erase what we have over here. So the outer radius would be from this point all the way down to the line. And the same strategies work for this as well. You could just do upper, meaning f of x, minus lower, which in this case again is -1. So that's going to come out to square root of x plus 1. And the second way works as well. This segment from just here to here, this is square root of x, and that length is 1. So square root of x plus 1 also just goes straight to that answer. Okay, so we've answered what they've asked for, but let's go ahead and write down what the volume would actually be. So the volume would be pi times the integral from 0 out to 1 again outer radius squared, so it would be that one first, square root of x plus 1 all squared, minus inner radius squared with respect to x. If you evaluate that one, this would be a little messy by hand. You'd have to foil all of this, combine as much as you can, but I believe you get 47 pi over 10 if you did evaluate that. If you did rotate this all the way around, it would have a hole going all the way through it, whereas when we rotated it in the previous one, no hole here. So similar shape, but with, obviously a hole passing all the way through. Okay, so what if we want to rotate a shape around the y-axis instead of the x-axis? Well, it's basically going to work the same way. We're just going to integrate with respect to y. So if we look at the picture here, I have two functions, q of y and p of y. We want to rotate them around the y-axis. So that means our cross-sections are going to be perpendicular to the y-axis. When we rotate it around, we're going to get a washer here. And the washer itself is generated by that segment, which notice is perpendicular to the axis of rotation. That is an important fact. So to get the area of that, we would need to do the outer radius squared minus the inner radius squared. So the a function would now be a function of y. It would be pi times outer squared. In this case, outer is p of y. So p of y squared minus the inner radius, which would be q of y, right? This distance here would be q of y. So that's our area formula. So then to do the volume, we would just integrate that. Volume would be the integral. Here's where we have to be careful. We're not integrating along the x-axis anymore. So our limits of integration, since we're slicing it up this way, would be from c up to d. So c to d, again, I'm going to go ahead and put the pi out in front of it. This is going to be the integrand. So p of y squared minus q of y squared dy. Integrating with respect to y now instead of x. So really the process is the same. It is outer radius squared minus inner radius squared. You just have to be careful, how you're identifying the outer. You have to kind of turn your head sideways, because if we were integrating this way, we would have called this function outer and this one inner. But when you're rotating it this direction, the one that's further away is here. This is actually outer. P of y would be outer. Okay, so that's just written out here. And then the last part of this is stating disk method still works as well, meaning that if there is no inner radius, then that formula works too. All right, so let's try this. So we have a function y equal x. That is just a line with a slope of 1. And then we also have the cubic function. So key points for the cubic function, 0, 0, 1, 1, and then negative 1 back here. So I can't get those. Would be something like that, and then obviously it continues over here, but the piece that we care about is what's in here. That's what we're actually rotating, and we are rotating it about the y-axis. So we're going that direction. So you have to kind of imagine it sweeping out a bowl here. This would kind of come back in the same direction. So our typical cross-section would be this direction here. I think it's always helpful to put this in. Whatever you're rotating about, your cross-section has to be perpendicular to that axis. Okay, now, since we've established that we're rotating about the y-axis, we're going to integrate with respect to y, which means we need these to be functions of y instead of x. So just solve them for y. Solve it for x. If we solve this for x, you get x equals cube root of y, and then that one's already solved for x. So let's just label it here so we don't forget. This is x equals y to the 1/3, and this is x equals y. So our volume is going to be the integral. Let's do pi out in front of it. We do pi because it's a solid of revolution. And limits of integration, we're slicing it from down here all the way up to here. So from 0 up to 1. Then outer radius squared. Outer radius is the one that's the further away from the y-axis, so cube root squared. So y to the 1/3 squared minus inner radius, which would just be y squared. Outer radius squared minus inner radius squared. You could simplify that, but let's just go to the answer. Didn't actually ask for the answer, I don't think, but that comes out to 4 pi over 15. Okay, let's try one more of these. So on this one, we're actually going to do two separate problems. We're taking this region, which is bounded by y equal x squared, x equals y squared, and x equals 4y. So I've already plotted those. We've got a straight line here, and we've got the... Oh, this looks like it's labeled wrong. So I think... Hold on 1 minute. Okay, I think it's just a typo up here. This should have been cubed. Okay, so we got the x equals y cubed, which would be the same as the cube root function. Like if you're doing y equals the cube root of x, same as this function you see here. So that defines a region, and we can rotate that region either about the y-axis, which would create this kind of hollow cone, or we could rotate it about the x-axis, which would generate a region like this. So the question is, which solid has the greater volume? Is it rotating about the y-axis, or is it rotating it about the x-axis? So let's find each one. We'll start with the y-axis. If we're rotating it about the y-axis, then that means our cross sections are perpendicular to the y-axis. So our volume will be pi times the integral. We're slicing it up this way, so it'll be from here up to here, which means up to the y value. This is where you have to be really careful, from 0 up to 2. Then we will do outer radius squared. The outer radius would be this function here, so it'll be 4y squared minus the inner radius, which would be this one here, so minus y cubed squared dy. And you can see that is actually over here as well. They wrote out this is just the a formula, but if you square this, you get 16y squared, and then if you square this, you get y to the 6th. Okay, so entering that in, that looks like it comes out to 512 pi over 21, which is approximately 76.60. Okay, so that's our volume for this hollow cone shape. So let's do the other one. So on this one, same region, same exact functions, but we're rotating it about x. So if we're rotating it about x, we have to integrate with respect to x, which means each of the functions have to be functions of x. So solve this, again, solve that for y, take a cube root of both sides, that's where you get this. Solve this one for y, which is where we get this function. So now volume is going to be pi times the integral from, we're slicing it up in this direction now. Cross sections are perpendicular to the x-axis, so it'll be from 0 up to 8. Notice the limits of integration changed. Previous one we integrated from 0 to 2 when we were rotating about y. On this one, since we're rotating it about x, we're slicing it up along the x-axis. Limits of integration are from 0 to 8. And then outer radius, this one will be the outer radius, so x to the 1/3 squared, minus inner radius, which would be the g of x, so x over 4 squared, and then this time dx. So you can see that is actually the same as this. This is just the a formula. They have the pi there, and then if you square this, you get x to the 2/3. If you square that, you get x squared over 16. Evaluating this one gives you 128 pi over 15. Which is equal to about 26.81. So we can see a lot smaller. There's a lot less volume for this shape than there was for this one here. Same exact region, but rotated in a different direction. Rotating it about the y-axis gave us a lot more volume than rotating the same region about the x-axis. Okay, last example. Last example is going to do something similar. We're going to use the same two functions, but we're going to rotate it about different objects. Sometimes I think we're going to do y equal 2, a horizontal line. Then we're going to do y equal -1, a different horizontal line. And then the last one we're going to do about a vertical line. So these are very common on the AP test where they give you a region, and oftentimes they don't even ask you to evaluate it. They just want you to set up the integral, not to evaluate it. Just set it up for a given scenario. Okay, so the first one, we're taking that region, which was bounded by the function f of x, and I guess we're not even using g of x on that one, just the f of x and the line y equal 2, and we're also rotating it about y equal 2. And looking at it just on the interval from 0 to 1. So if you visualize this thing rotating about this line y equal 2, you can see that it's going to be solid. There's not going to be a hole inside of it. So we don't have to do outer and inner. It's just radius squared. We just need to figure out what the radius is and square that. So volume is going to be pi times the integral from, we're slicing it up in this direction, so 0 to 1, times the radius squared. So let's just write that for now. Radius squared, and it will be dx because since we're rotating about a line that is parallel to the x-axis, which means we are integrating with respect to x. Drawing in that typical cross-section again is very helpful. You can see that shows we're slicing up the x-axis, and when that gets rotated around, you'll get a circular disc here. Okay, so let's come back and try to find an expression for the radius. So to do the radius, we can again do upper minus lower. So when I say upper, it would be this point here. Well, that point's along this line. You could think of this line as a function. That function is 2, right? It's g of x equals 2 if you want. So this could be 2 minus lower, this is the lower. So lower would be f of x in this case. In other words, it would be 2 minus the square root of x plus 1. The other way to visualize this is to think about, well, the 2 represents this entire segment. I don't want that entire segment. I need to get rid of part of it. And the part that I need to get rid of is this. And that pink part is f of x. Right? The green part, this whole thing is 2, but 2 is too much. It's all of this. I want just this part. So 2 minus the f of x. That's where this is coming from. Okay, so if we cleaned that up, we distribute the negative, and then we can combine those like terms. You get 1 minus the square root of x. That is the radius. So our volume is going to be pi times the integral from 0 to 1 of 1 minus the square root of x, that quantity squared, dx. So that expression should be the volume created by that solid of revolution, and that volume comes out to pi over 6. Okay, next one we are introducing that g of x. F of x stayed the same, so we still have that graphed here. Square root function just shifted up 1 unit. And then we have the square function shifted up 1 unit. That creates a region R, and we are going to rotate it about y equal -1. So first thing to try to identify is, are we integrating with respect to x or with respect to y? And that's where drawing in your typical cross-section helps. So that if we're rotating it in this around this line here, your discs are going to be, created like that. In this case, it's technically a washer. So you can see that those are perpendicular to the x-axis. So we are going to be integrating with respect to x. So that means we're going to do volume is going to be pi times the integral from this point to this point, 0 to 1. That's what we're slicing up. And now we need to do outer radius squared. So the outer radius, let's actually write that down up here. Outer is going to be upper minus lower. Upper would be just f of x, minus lower is a negative 1. So if we put all that in there, this is really square root of x plus 1, plus 1. So that represents this entire distance. And again, you could think of it differently. This is just f of x, but then I have to keep going, and that additional distance is 1. So that outer radius is f of x plus 1. Okay, let's do inner radius. So the inner radius would be the distance from here all the way down. So again, you could say upper, which would be g of x, minus lower, which again is negative 1. So this is really g of x plus 1, which is going to be x squared plus 2 when you add these two together. So that's the g of x, you're adding 1 to it, just like the previous one. Okay, so this gives us everything we need now. We just need to do this thing squared minus this thing squared. So square root of x plus 1 squared minus x squared plus 2 all squared dx. All right, again, to do this by hand, you'd have to FOIL here, combine like terms, and then integrate. This should come out to 49 pi over 30. All right, last example, same region as the previous one, but we're now going to rotate about the line x equals 2. So let's start by identifying the outer radius. So as with the previous, we can do upper minus lower. Now before we do this, I guess we should identify what we're integrating with respect to. If we're rotating around this x equals 2, notice that the line is parallel to the y-axis, which means we're going to integrate with respect to y. Our typical cross-section is going to be drawn perpendicular to the y-axis. So that we need to know that in order to identify what is actually upper and lower. So you kind of have to turn your head to the right, and that means that this is above this. This is upper, this is lower. So if we look at the functions, think of this as its own function, x equals 2. The outer radius is this distance here. Right, that entire segment. But this would be upper, and this would be lower. So it's going to be 2 subtract this function here, which is, I'll also notice, to get these functions, I had to solve them for x, because we needed, if we're going to integrate with respect to y, they have to be solved for x. So this curve represents this one here. So we're going to do 2 minus y minus 1 squared, upper minus lower. The other way to think about it is the entire distance here is 2, and the function itself actually represents this segment. This expression is the length of that segment there. So we take 2 and remove this piece, which leaves us with this segment here, which is actually the radius that we want. When we rotate it here, that's the outer radius. So 2, take away that. 2 minus that function value. Okay, let's do the inner radius. So inner radius would be this length here. So again, you can think of it as upper minus lower. Again, with your head turned to the right there. So upper is still 2. Right? This is above both of the functions, and lower would be that function itself. So minus the square root of y minus 1. So we have each of the radii given there. Outer radius, inner radius. So the volume is going to be equal to the pi. Don't forget your pi. Pi times the integral from, limits of integration are here. This is what we're slicing up. So from 1 to 2 of the outer radius, so this thing, all squared, the whole outer radius squared, minus the inner radius squared. With respect to y. So it looks really messy, it is complicated, but it is using the exact same methodology as the other ones. This is just your washer method. We've got pi times the integral of outer radius squared minus inner radius squared. If you evaluate that, that one comes out to 31 pi over 30. And I believe that's the final example. It is. So hopefully this made sense. Email me if you're having trouble with the homework, and we will see you on the next video.